Okay, so thank you for this kind and long introduction, which makes me feel very old. So first of all, thank you to all the students for inviting me. It's really a pleasure to be here. So I just made a very last-minute switch of my presentation. I had a very, let's say, high-level and divulgative presentation, but I think given the audience, probably you will enjoy a little bit more technical one, more close to my research activity. So that's why the topic is a little bit different. So you already know who I am, what I did, so let me dig directly into the topic. So we're going to talk about quantum technologies. And when we talk about technologies in the quantum framework, we typically talk about communication, cryptography, computing. Now there's a big hype on quantum machine learning, quantum artificial intelligence, and quantum sensing. So there's a lot of expectation on quantum technologies. I find this title a little bit pressing. So quantum technologies can help to tackle climate, hunger, disease, whatever. So it's maybe too much, but we'll do our best. Okay, so the platform with which you can do quantum technology are very diverse. You can have superconducting qubits, trapped ions, cold atoms, defects in diamonds, but last but not least, photonics, and that's the one we are going to focus on today because it's the International Day of Light. So what can you do with quantum photonics? As I said, you have different application topics in quantum technologies, and photonics can cover more or less all of them. And that's quite a specific feature of this platform with respect to all the others. You can do communication. Of course, photons are the only flying quantum objects that preserve their quantumness over long distances. So you can do quantum communication. You can also do quantum sensing. Here is an example of the LIGO gravitational wave interferometer. You can also do, as I mentioned before, quantum machine learning with photons. But today, I mean, what I'm going to focus on is quantum computing. So that's going to be my main focus today. And the angle with which I will talk about photonic quantum computing is with integrated photonics. So why integrated photonics? That is an example of an optical table where you do discrete optics, quantum experiments, and you can appreciate the complexity of the mounting. The beauty of integrated quantum photonics is that everything shrinks on a very small piece of solid state material where you have all the components inside, and most of all, it's very much mechanically stable, so vibrations are not a big issue, which is indeed a big problem for quantum experiments where you want to keep the phase stability of the overall experiment to a very high degree. So having everything on a single piece of material helps a lot in that direction. It is also highly scalable. You can add a lot of components on a piece, on a photonic chip, while making it in discrete optics can be cumbersome due to the alignment, which become more and more complicated. And last but not least, of course, if you want to bring these technologies outside the lab, integrated photonics can be mass-produced and can be really delivered to real application and not just lab experiments. Okay, so what we do now, a little bit on what is my research activity, is to make these integrated quantum photonics not with standard photolithographic technologies, which you may be familiar with, like silicon photonics, silicon nitride, whatever technology where you have a thin layer of inorganic material, you do photolithography to define the circuits. In our case, we use glass as a starting material, and we use femtosecond laser pulses, so very short laser pulses, which we focus inside the transparent materials. And given to the fact that we have a lot of photons coming to the same point at the same time, because we are focusing very short pulses, we can induce nonlinear absorption processes. So we can deliver energy in a very localized way, just at the focus of this laser spot. And by doing this, we can induce permanent modification in the material, which, if you tune right the radiation parameter, can become an increase in the refractive index. And that is the building block. If you now translate the sample with respect to the laser, you can basically write photonic circuits. Okay, so it's a direct write technology, it's maskless, and it's 3D, so it has a lot of potential. So let me actually have a dedicated slide on that. So as I said, it's maskless, so you just program your circuit, you program the movement of the stages with respect to the laser, and that allows you to make arbitrary layouts, which you can easily change by changing the software. You don't have to redo the mask every time you change everything. And that is quite nice if you're going to do fast optimization of your devices. You don't have to spend 6 months in doing all the simulation and making the tape out and then sending it to a foundry and then to learn that you made something wrong and you have to throw it away 100,000 euros and you have to start again. In this case, you fabricate one device in a couple of minutes, you go to the lab, you check it, and you say, okay, I have to change this thing, you change the software, go back, and so the iteration is much faster. It has 3D capability that's quite unique. You can write waveguides at different depth in the glass because the absorption is very localized in the focus spot, so you can put the spot anywhere you want in the depth, and you can even move in the 3 directions. So it's not only that you can make several layers, you can really make a circuit that goes up and down, so it has really a 3D shape. And this you can exploit in many applications. You can control the polarization states on chip. You can make deformed waveguides which become birefringent. You can rotate them, so you can play a lot with the polarization on the circuit, which is something you cannot do with standard photolithographic circuit, which typically are highly birefringent and they only work with a single polarization. In this case, you can use the polarization degree of freedom as something to encode information, to manipulate information, and so on and so forth. Last but not least, you can also process different materials. So this technology, this direct writing technology, actually works on any transparent material. So we work on glass where we have the best properties of the circuits, but you can also do it on crystals, for example. So you can write waveguides in crystals, you can do nonlinear optics in waveguides that you write in crystals, and then you can also couple all them together, as you see here on the bottom right, whatever. And you can make a hybrid device where you have passive and active components on the same one. Okay, so now let me go back. Now I a little bit dwelled on the technology. Let me go back on the main application I'm going to discuss, which is quantum computing. So the first step in the roadmap to quantum computing, which is sorry to say not tomorrow, so we need still a few years. So the first step is so-called quantum advantage. Now I'm going to discuss what this is. So if you go on Wikipedia, which is of course the first source for any scientist, and you look for quantum advantage, it says quantum advantage is the goal of demonstrating that a programmable quantum device can solve a problem that no classical computer can solve in any feasible amount of time. So basically the quantum advantage is when you have a quantum device that can do better than a classical one. Okay, so it seems like trivial. If you read on the newspaper, it seems that we have done it already 100 times in the last 10 years, but it's not like that. So it's still a challenging task. And I want to highlight a couple of points. One is that the device should be programmable. And on the other hand, it doesn't say that you should do something useful. Okay, so quantum advantage is not saying you're doing useful stuff better than a classical device. It's just saying you're doing something better than a classical device. Okay, that's a subtle difference, but it's important because that's the first step. Okay, of course we want to do something useful, but that is going to be the second step. Okay, good. So now talking about quantum advantage, which in the early days was, well, not so early days, a couple of years ago was called quantum supremacy. Then for, let's say, politically correctness, I mean, supremacy is not a good word, so they switched it to quantum advantage, but you can still find it on some papers. So this was the first paper that claimed quantum advantage. Okay, that's a Google paper from Google. They use superconducting circuits. They implemented an algorithm which is completely useless, doesn't solve any problem, but they claim that solving that algorithm with the 54 qubits, superconducting qubits, would take 10,000 years for a classical supercomputer. So they claim, okay, that's a clear quantum supremacy. Okay, I'm solving something useless, but something that can take an almost infinite time for a classical supercomputer. Okay, that was remarkable. It raised a lot of attention. The problem with the quantum advantage is always with what you compare to. Okay, so of course you're saying I have a quantum advantage because I can do better than a classical computer. But are you sure that you're exploiting the classical computer at its best capabilities? Maybe you're just comparing with a very crappy algorithm with a classical computer. And in fact, after this publication, then a lot of people working on classical algorithms started to dig into this problem, which was weakly studied because it was useless. But now they have a motivation to study it. And so a couple of years later, in 2022, this Chinese group came up with an advanced classical algorithm saying that the same problem could actually be solved in 5 days. Okay, so the quantum advantage now becomes a little bit shady, it's not so clear. And then again, it's the International Day of Light, so it's good to emphasize that the only other 2 experiments that showed quantum advantage were actually based on photons. Okay, so the first one was on superconducting qubits, but now we also have 2 with photons. This first one, which was done just 1 year after the Google experiment, is done in China, in Hefei by Zhang Weipan's group. And that's really a monster experiment. This is done all in discrete optics. You see a picture here. There are thousands of lenses and components that have been aligned very carefully. So only Chinese probably could do this. And the problem that they addressed is called Gaussian boson sampling. Okay, that's a problem we are going to discuss a little bit more because it's specifically tailored for photonics. Again, they say 2.5 billion a year for a classical computer. So, okay, we're waiting for classical people to say, well, maybe a little bit less than that. And then there's another example just for completeness, so no one gets upset. So this is a more recent paper, 2021, from Xanadu, which is a company in Canada developing quantum computing. And they also managed to achieve quantum advantage with photons, with this hybrid approach with fibers and fast electro-optic switches. Okay, so that's more or less the state of the art on the quantum computers. Let me now dig a little bit more into the boson sampling problem, which was the one that enabled to demonstrate a quantum advantage with photons. Okay, so why do we study the boson sampling problem, which, as I already more or less mentioned, it's a useless problem. So it doesn't solve any, I mean, so far we haven't found any good problem that is solved by this algorithm. I mean, just to be clear, I'm not downturning it. So it's a massive objective to demonstrate quantum advantage. I'm not saying that, okay, who cares about these experiments? I mean, those are really key experiments because this is the necessary step to be able then to do something useful. If we don't get quantum advantage, of course, we can study whatever useful problem, but will never beat the classical computer. Okay, so just to emphasize that this is actually the most important thing we can do at the moment to demonstrate this quantum advantage reliably and with more and more resources. So why don't we just tackle Shor's algorithm? So that's a very famous algorithm for a quantum computer that can factor large integers. And if you can implement the Shor's algorithm on a quantum computer, you could crack basically all the cryptography that is used nowadays. Okay, so that was a strong motivation to develop quantum computers. On the one hand, to try to crack the encryption and get a hold on all the information that's going around the world. And on the other hand, it's also stimulated the quantum cryptography field. So why don't we just work on this? Well, it's not really current, it's a little bit dated, but let's say in 2009 it was to factor 15. So that was the best you could implement with the resources they had available. I think more recently they factor 21, okay? So to really implement Shor's algorithm, you need 1 million qubits. So it's still too far away with respect to what we have now available. So that's why we're now targeting a more close by goal, which is to demonstrate quantum advantage. So boson sampling was really a big achievement, which was proposed by Scott Aronson from MIT at the time, which is a problem that has some theoretical demonstration that is hard for a classical computer, but can be tackled with a quantum system that has a level of resources that is affordable nowadays. So that's why it is so important and why it was used in the two demonstrations that I mentioned. So what is it, this boson sampling problem? So you can have a classical equivalent, which is the Galton's board. It's a game in the 1900s that they used in England. So the game was to have this kind of board, wooden board with nails, and then you just drop metal balls, and then they would just jump around in these nails and then get out in these outputs. And then if you drop sufficient number, you start to see the probability distribution that you have at the output, which in this case, it's just a binomial distribution. So if you make, you schematize this, you have an initial state, which is where you put the metal ball at the beginning. You have a transformation, which is all these nails that you have on the vertical wooden board. And then you have your output distribution. So you can have an equivalent in a quantum system, which uses bosons. So that's why it's called boson sampling. So you have n bosons, which you can already imagine in our case will be photons, but let's be general so far. So you have n bosons, you input them in a given number of inputs, then you have a randomly chosen unitary transformation, and then you have your output distribution. So the problem that you need to solve is, given the input state and given the unitary transformation that you randomly choose, can you sample from this output distribution? So can you produce samples that respect the probability distribution that is created by this experiment? So this seems simple, but it's actually a very hard problem to solve. Why is it a hard problem? The reason is that if you use bosons, and that's why it is important to have bosons and not fermions, if you have bosons and you want to compute the probability, the output probability, if you apply transformation to a set of bosons, you have to calculate the permanent of the matrix that represents your transformation. If you use fermions, you would have to calculate the determinant of the matrix. Calculating the determinant is very efficient on a classical machine. You can calculate it pretty nicely. If you calculate the permanent, where the permanent is just like the determinant, but you don't change the sign every now and then. And so if you calculate the permanent, that is demonstrated to be a Sharp-P complete. So it means computationally very hard for a classical computer. And so if you have to solve the boson sampling problem with a classical computer, you would have to calculate the matrix permanent, and then you have to repeat it for all possible combination of input and outputs. And then once you have retrieved the full probability distribution, you can sample from it. And that is hard to do. You can do it with a quantum device rather intuitively, in particular with a photonic device. In this way, you can have photons, which are your bosons, input bosons, and then your linear unitary transformation that you have to implement, which you can produce by having a suitable mesh of bin splitter and phases, and then you just acquire the photons at the output, and that would automatically gives you a sampling from the output distribution. Okay, so it's of course it's not a universal quantum computer. It's very specialized. It only solves a very specific problem, but still it does it very, very efficiently. And so that's why it has been used to demonstrate the quantum advantage. So going back in time, I mean, with respect to the latest demonstration of quantum advantage, the first
demonstrations of boson sampling at a much smaller scale, so not yet at the quantum advantage level, have been done on photonic platforms, and I have to evidence that 2 of them were actually based on femtosecond laser written circuits, just to show how powerful this technology is. And one of them has been done by us. So let me give a little bit more insights into this. So you can demonstrate, now I'm not going into too much details, but you can demonstrate that an arbitrary unitary transformation can be always decomposed with this kind of mesh. And that was the first kind of decomposition proposed in this paper, where you have a triangular mesh where you control transmissivity and phases. So if you can control transmissivity and phases in your circuit, you can implement any possible transformation with a very well-controlled way. And so what we did is to actually write the circuit with the femtosecond lasers, and we could control transmissivity and phases by controlling these 2 areas, the yellow and the blue area. So the idea is that the blue area corresponds to a so-called directional coupler in integrated photonics, which is a device where wavegates couple, and it's equivalent to a beam splitter. And so by controlling the level of interaction in this device, you can control the splitting ratio, so the transmission of the node. And the phase, you control it in the yellow part. So let me start with the beam splitter, let's say the directional coupler. So how do you control the transmissivity there? So one way you could think of is I just separate the 2 wavegates more or less, or I make them longer or shorter, and that would modulate the transmissivity. But that would also deform the waveguides before and after, which will introduce a phase, an unwanted phase in your circuit. So the way we did is we took advantage of the 3D capability, and if you see in panel C down here, so if you look here in panel C, you see what the idea was. So we just rotate out of plane, we fabricate one of the 2 arms out of plane, rotate a little bit, and that would modulate the distance between the 2 waveguides that are coupled, so we can control the coupling coefficient, and then the transmission, as you see here, we can control the transmission from 0 to 1, but we are not deforming the circuit around it. So we can control transmission without introducing a phase shift. On the other hand, to control the phase shift, we now deform the waveguide that gets to the coupling region. And there we just change the shape, which changes the length that light has to propagate through, which changes the phase that is acquired. And again, you see here the calibration, and you see we can get easily a pi phase shift, which is what you need. Okay, so with this experiment, then we went to do the actual boson sampling experiment with SPDC sources here, generating 4 photons. One is the trigger, the other 3 photons, they go inside the circuit, and then you sample at the output by taking all outputs and going to different detectors, and that would allow you to actually measure where the photons are coming out, and that is really doing the boson sampling experiment, which is sampling the outputs on a given probability distribution that is given by the circuit. So here is experimental results compared to theory. You see that it actually behaves pretty well. We then scale it up from 7 modes to 9 modes to 13 modes, and you see that the agreement is still pretty good. One point I want to briefly touch, I don't want to spend too much time on this, is the validation. So one thing that is often, let's say, underestimated is that we're building, hopefully, quantum machines that have quantum advantage, which means that will solve problem that we will not be able to solve with a classical computer. Then the question is, how do we certify that the quantum computer is really doing what we are expecting? So that is validation or certification problem, which is not easy to solve. So we did some work in this direction.
trying to find ways that can certify that the quantum machine is indeed behaving properly. And just to give you a hint on this, so I would say a first approach would be to do what you would do with a classical computer once you write a new software. How do you know that your new simulation software is doing what you're expecting? Where typically you apply it to a known problem, you see if the solution is what you expect, and then you apply it to an unknown problem, hoping that the machine will work as well, and that will give you reliable results. So the idea here is that if you want to do a given quantum computation in a quantum advantage regime, which you cannot benchmark on a classical computer, then what you would like to do is to have a different circuit which is easy to compute and to calculate and to know what to expect. So you apply this circuit, this simpler, let's say, circuit. Then you verify that everything is working properly, you get the result you expect, and then you change the transformation to the new one, and then you hope that everything is working the same. So for doing this, you need to have programmable devices, because you want to change then having the same setup, but changing from a transformation for which you know what to expect to a transformation for which you don't know what to expect. And so that's a further motivation to go to programmable devices, which is what is written here. So tunable circuits are needed. And so we move towards universal processor for linear quantum photonics. So with universal, what I mean is a linear transformation that can be arbitrarily chosen. So let's say whatever transformation you choose, you go to this photonic circuit, you program it, and you can implement it. So what you have seen before were static transformations. So we were writing the circuit with a given transmittivity, a given phase, but those were fixed. Once we write them, they're there. We cannot change them. So we have to find a way to program the circuits. We have to do it with low losses, because losses are a big issue. Now, I don't want to discuss this. But you have a few requirements you have to take care of. So the actual architecture now is a little bit different. It's no more triangular, it's rectangular, but conceptually is the same story. So you have an architecture which can implement any arbitrary transformation on that number of modes. What you have to do is to control in each node, which is actually this, so a Mach-Zehnder interferometer. What you have to do to be really universal is to control in each node these two phases. The internal phase, which controls basically the transmissivity of this equivalent beam splitter, and the external phase, which is the other phase we need to control. So by controlling two phases per node, you can implement any arbitrary transformation. Okay, so how do you control these phases? So there are different ways. The most popular way is to use thermo-optical phase shifters, which work like this. So you have, so here is how we do them with our technology, with femtosecond lasers, but you can do them with photolithography as well. But the idea is that you have your circuit made in glass, which you write in glass. Then you deposit the metal on top. Then we do it with the laser, because then it's nice, it's all maskless. With the laser, you can etch the metal, and you can define the electrical circuit. And then by changing the shape of this circuit, you will have here a low resistivity area, and here a high low resistance area. Resistivity is given by the gold. So this is low resistance area, and this is a high resistant region where you have very narrow circuit. And why do we do this? Because in the very narrow part, you have high resistance, high Joule effect. So you dissipate a lot of heat there, which you don't dissipate where you have low resistance. So by doing this kind of circuits, you can localize where you're going to heat up your circuit by the Joule effect. And then the dissipated heat
will propagate in the material below and will heat up the glass, will heat up the waveguide. And since the refractive index of the material depends on the temperature, if you increase the temperature, you increase the refractive index, which means that light propagating in that portion of circuit will experience a phase that depends on the refractive index. So it depends on the optical path. So the length times the refractive index. And so in this way, you have a way to control actually the phase in that portion. Is it clear? Okay, so you can place many of them around the circuit, and by doing this, you can control all the phases that you need to control. So here is an example with a single phase shifters in a Mach-Zehnder, and you see that by controlling dissipated power down here, you can very nicely control the output distribution with very, very high visibility. And with fringe visibility 99%, you can do even better than that. So another issue we faced is that to get a full 2 pi phase shift, you have to dissipate half a watt on a single thermal shifter. Now, if you want to make a very complicated circuit, you may need to put 500, 1,000 thermal shifters. So if you have half a watt for each of them, this is going to be like something that heats the room. So it's not something that you want. You want to keep control on the temperature and all this. So you want to scale down the dissipated power. How can you do this? So again, femtosecond lasers. So you use, this is the standard scheme with the planar layout, the cross section. The two blue points are the two waveguides of the Mach-Zehnder. The yellow bar is the thermal shifter. So if you don't do anything, you have the heat dissipates around. You want to heat up only this waveguide, you're going to heat up the other waveguide as well. And so before you get the pi difference between the two, you have to dissipate a lot of power. That's why you need to dissipate half a watt. So if you do laser ablation, you create trenches around the waveguide which you want to heat up. This will limit heat diffusion around here. You will confine the heat right where you need it. So this one can remain more or less cold, and with much less heat, you can get a pi phase shift between the two. You can even go with the bridge. You can do under etching, and that further confines the heat and lowers the heat dissipation. And those are microscope images from the end facets. You see, these are the trenches that we can produce, very high aspect ratio, 300 micron deep and just 50, 60 micron wide. And here, of course, you cannot see, but the waveguides are right here at the top here, right below where we put the thermal shifters. And the other picture is a top view. And so if you do something like this with the trenches, you get the same 2 pi phase shift with at least 1,000 times less dissipated power. And here you see more or less a summary. And so with the planar layout, half a watt. The other problem is the crosstalk. So you have densely packed elements, thermal shifters. You want to heat up on one Mach-Zehnder, but heat diffuses around. And so all other Mach-Zehders are going to be affected. Crosstalk, it's a mess. So you have to really map all this crosstalk and try to live with them. So, and you see here, it's pretty high, 70%. So you heat up one Mach-Zehnder, and the other one, which shouldn't be touched, actually has 70% of the phase that you have implemented on this first one. So if you go with trenches, you go from half a watt to 38 milliwatts, and crosstalk is heavily diminished. If you go with the bridge, you still have a further improvement. And what is limiting you here is still air that you have around. So you have diffusion in air. But if you go and you put this in a vacuum chamber, then things get even better. So if you look at the bridge results, which is the highest confinement you can get, you go from half a watt to 1 milliwatt per element, and crosstalk becomes negligible. So there you have really neat control of what you are implementing. You say, okay, it's a vacuum chamber, but you don't have to bring around a vacuum chamber. There are ways to encapsulate your device and keep it in vacuum and make it very compact and transportable, which is what we're doing, by the way. So, so here's an example of a 6-mode processor with all the trenches, the thermal shifters. You see also a picture of one of the first generation ones. I'm not going into the technical details, just showing you
some calibration. So given that we now have a very good control of what's going on, we can do permutation, so we can have any input going to any output, and we can program it pretty nicely. The figure of merit we use is this fidelity, which is defined here, and which is basically the overlap between the output distribution that you want and what you are getting. And you see that the fidelity is above 99%. So basically we have exactly what we want. Okay, so that was, let's say, trying to summarize more or less where I've gone so far. So we discussed quantum advantage, which is not going to be a universal useful photonic quantum computer. It's just first step. I've discussed that anyway, you need programmability because you need to implement randomly chosen transformation to demonstrate quantum advantage. You need it for validation. So there are lots of reasons why you need this. And in fact, we have it. Now let's move to making a real universal quantum computer. Can we make it? What is the path to that? So here I call it the photonic way to quantum computer, because among all the platforms that we mentioned before, superconducting qubits, ion traps, photonics are a little bit special. They are different from the others, and I'll briefly mention why. So just to give a very low level, let's say, low in terms of quality, not really in terms of components, discussion of how universal quantum computer works. So you have a quantum register with all your qubits. Then you apply your transformation to these qubits. You have your circuits that apply this transformation. And then you have your n qubits at the output, which you have to measure to get the result of your computation. Okay? So pretty standard architecture. That's more or less what you have on a classical computer as well. You have a register with bits. You have a microprocessor that makes the operation on the bits. And then at the end, you read out the register and you get the result. The only difference is that here you have a quantum register, so you have qubits which stay in a superposition state, which is this weird possibility of staying in multiple states simultaneously. But then to get access to the information, you need to measure, so you need to collapse this state, and that creates a lot of issues which I'm not going to discuss today. So how do you do the quantum circuit? So the way you do it with a classical computer is to use logic gates. I think you're all familiar with classical computer. You have all these logic gates, and you have a minimum set of logic gates that allows you to make any possible transformation, any possible computation on your classical computer. Okay, you need I don't remember, but just a few of them. So is there a similar thing in a quantum computer? Yes. So there's a minimum set of transformation that you need to do to be able to implement universal computation with a quantum computer. What is this minimum set? You need to be able to implement all possible single qubit gates, which are very easy. So you have one qubit, like a single photon in a given state. You imagine that you encode your information, your qubit in polarization. Okay, so you have H, which is 0, V is 1. Okay, that's your single qubit. You need to be able to manipulate the qubit in any possible way. And that is easy. You just put wave plates, retarders. You can really prepare the state in any point of the Bloch sphere that represents the polarization state of that qubit. So that is good. And then, but that's the sad part, you need a 2-qubit gate. Okay, you need at least one 2-qubit gate, where a 2-qubit gate is a logic gate. You see here one example. So that's a 2-qubit gate. That's a C0 gate, which is a NOT controlled on the first qubit. So depending on the state of the first qubit, you want to apply a NOT gate on the second qubit. Okay, so basically, these 2-qubit gates are entangling gates. Okay, they have a lot of properties, and they are key elements. If you don't have these 2-qubit gates, it's hard to make a circuit-based quantum computing mimicking what you do on a classical computer. Okay, so that's what you need, and that's what all the other platforms are doing. So you can do 2-qubit gates, you can do C0 gate or similar 2-qubit gates on ion traps. You can do them on superconducting qubits. It's hard to do them on a photonic computer.
Why is that? Because to make a 2-qubit gate, which you see here, like the CNOT gate, what I was mentioning before, is something where if the control qubit is 1, then the target qubit flips. If the control qubit is 0, the target qubit doesn't flip. So that's the basic idea. So why is it difficult to make this? Because you have to implement photon-photon interactions. So you need to change the state of a photon depending on the state of another photon. To do this, you need photon-photon interaction. And we don't have yet a nonlinear material that is so nonlinear to be sensitive to the state of a single photon. Okay, there are ways. I mean, people are working on putting these single photons into quantum dots and then playing with this to make nonlinear gates, but it's complicated. It's not easy. So you can still do these 2-qubit gates, and this is something that we have done a long time ago with photons, but I mean, I don't have time to give too much details on this, but the key point is that you can do 2-qubit gates with photons, but it is a post-selection process, which means that it's not a deterministic operation. You have to do it, and you have to do it many times until you get exactly the configuration that you like, and then you can say, I've made the 2-qubit gate. But that, of course, is not scalable. If you imagine to concatenate thousands of these 2-qubit gates, then having all of them behaving properly becomes very, very unlikely. So that's not the way to go. And so let me move rapidly to actually the special way that is actually followed nowadays by the photonic quantum computing platform, which is no more going for the circuit model, which is this one here. You may be familiar, you may have seen it, which is just concatenating single and 2-qubit gates, which is what, as I said, other platforms are doing. In the case of photons, since it's complicated to make the 2-qubit gates, what people is trying to do is to start with a different state. So while with the circuit model, you start with single independent qubits, and then with the computation, you entangle them, you manipulate them. With the photonic approach, you start with a quantum cluster state, which is a state that it's already highly entangled. So you start with this kind of things where you can say that these are all photons, single photons, and the lines are the entanglement. So they are very much entangled each other. And since you start already with a highly entangled state, then you can do universal computation with just single qubit gates. And then you just operate single qubit gates, you measure, and then you have to do feed forward. So you have to optimize the next measurement depending on the previous one. So it's not trivial, it's still a complicated way, but it's a hard way for everyone. So that's sort of comfort. So basically the photonic community shifted the problem of implemented 2-qubit gates in the computation. They shifted the difficulty in generating a cluster state at the beginning. If you're able to produce this cluster state, then the computation is very easy. Well, it's reasonably easy. But making the cluster state is where people is putting now a lot of effort. So you have to really generate all this photon highly entangled. But the difference in having this difficulty in the computation is that you don't have to repeat the computation 1,000 times and wait for the result. You have to repeat the generation of a state 1,000 times, and this you can do it in parallel on many sources. And then once you have one ready, you feed it into the computer, and then the computation is deterministic. So that's the kind of idea behind it. And this kind of cluster state, you can produce it by using as building block G at Z states, so Greenberg, Horn, Zeilinger states. This is probably getting a little bit too technical. So I don't know if you're familiar with entangled states. The well-known states are the Bell states, which are 2 photon entangled states. These are more than 2 photons entangled states. And but okay, I think I'm out of time more or less, and maybe that's a little bit too technical. So let me skip this. And with this, I jump to the conclusion. So I hope I have more or less convinced you that integrated quantum photonics has a lot of potential. Actually, in many applications, I just mentioned computing, but of course, you can imagine it's very powerful for communications, as well for sensing and all possible technologies in quantum. And then I also mentioned our specific technology, femtosecond laser writing, very powerful for fabricating circuits very rapidly with unique 3D capabilities. And then as a final remark, let's say the path toward universal fault-tolerant photonic quantum computer is still long and full of hurdles, but yeah, I mean, we're all working toward that, and I think it's something that it's a big goal, but highly rewarding if we get there. So thank you all for the attention.
Thank you very much, Professor Osellame. Are there any questions?
Maybe said by the last one. When you have the tranced waveguide, I think you also improve the speed of the modulation.
So that's a very good point. It actually worsened the speed. So that's the final column, which I didn't highlight, so you wouldn't see it. So it actually worsened and that you can understand intuitively, because if you are confining the heat in a specific region, then when you want to take it out, it's also rather difficult. So the switching becomes slow, because the more you isolate the region, the harder it is then to take away the heat or to change fast the temperature. And so it actually worsened. The point here is that in any case, 10 milliseconds is not really fast. So if you want to do fast switching, you have to change technology. You shouldn't go for thermal shifters. And in fact, we are developing other phase shifters to go fast. If you are in this region here with a thermal shifter, the idea is that you want to program your circuit and then keep it steady for some time, acquire statistics, do experiment, and then change it again. And then if you keep it there for maybe 5 hours, 5 days, as in some experiments, waiting 10 milliseconds or 1 second doesn't really change. So that's the point. But yeah, that's a good comment. Yes, please.
Thanks a lot for the great presentation. How long does it has to be the let's say the modulated part to actually have a 2-pi phase shift in these chips? And
Was it?
and at the end, how big a typical chip is compared to other platforms?
Yeah, that's also a very good point. So let's see, I had a picture. So the length of the thermal shifter, that depends on how high the temperature you want to have. So in principle, you can have very short thermal shifters that have very limited space or travel range to introduce the pi phase shift, which means that you have to raise the temperature a lot. And that may have issues in terms of reliability, that they do not burn. You know, this thermal shifters, they are like 10 micron large. So if you pass too much current, then at some point they may just break. So typically the length that is used is in the order of 1 millimeter. So that's the order of magnitude with any technology, let's say our or any other technology. Regarding the overall length, so that's another important point. So in our case, circuits are in the centimeter scale, while with other technologies like silicon nitride, silicon photonics, they are in the millimeter scale. So we are an order of magnitude larger, but we have we compensate for that with two aspects. One is that size doesn't really matter so far in quantum computing, in the sense that if you have a working quantum computer that is 10 times larger, I think anyone would buy it and not say, oh no, I want it smaller. Okay, so I mean, that's not yet a problem where you have a personal quantum computer. At the end, what really matters are the insertion losses overall. So for photons, decoherence is not really an issue. The issue is photon losses, which is our decoherence. So what you really care are the photon losses. So in our case, we are longer, but we lose much less photons. So at the end, it's not a drawback. And the reason why we lose less, you can imagine, it's glass. The confinement is very similar to that of a fiber. So once we move from a fiber to a circuit, the losses are very, very low. While with other technologies, you have a much higher index change, dimensions are very different. There's a lot more of engineering to not lose in the interface. Okay. Please.
I ask you again about the thermal control of the circuit, because it's clear the switching is not easy, it's not fast, but even keeping it stable, it seems to me to be kind of problematic. I mean, if you just keep on giving voltage, delivering the energy that you have to dissipate, I mean, keeping a thermal equilibrium with an uniform kernel distribution is not easy. So what are the strategies to control stable
yeah.
performance?
So let's say actually it is very stable. So our devices, they work for a month without being touched. Of course, you have to stabilize the temperature at the bottom. So we have a Peltier that stabilizes the bottom temperature, but apart from that, it automatically goes to a steady state. And let's say even the fact that they switch lower is actually good, because they actually filter out any possible high frequency fluctuations. So they're very stable, not only in the long range, but even the short range, they are extremely stable. So the point is that, of course, you have some dissipation somewhere, so you're never able to completely isolate your waveguides, just because it is indeed a continuous waveguide. So if we make a bridge, you have to imagine this beam of glass suspended, but at the two edges is connected with the rest of the glass. So that's a dissipation channel. And so we dissipate very little power, and this power goes off that way. And it rapidly in 600 milliseconds, it reaches the equilibrium condition, and then it remains extremely stable.
So the C is source, processing, and detection. Can you comment if you think that you can combine source and processing and detector? Is there sense in doing this? So is that to leave there?
Yeah, that's a very good question. I've been asking myself several times, but so let's say so there are different strategies, of course. Each one has pros and cons. So there are platforms, for example, silicon photonics platforms, where they try to put everything on chip. And the reason is mainly because it's very costly to go out of the chip. So you lose a lot of photons in going out. So you better have everything on chip. So they typically do linear sources, four-way mixing rings on chip. And then they also try to put detectors on chip. That has some drawbacks, which is, for example, detectors, they are typically superconducting nanowire detectors, which means that to have them operate at the right range, you have to cool down the whole thing at a few Kelvin. And then having thermal shifters may not be the best at a few Kelvin. So there are engineering difficulties in doing this. So far, since, let's say, one of the nice things about photonics is that you can process at room temperature, which you cannot do with other platforms. It's nice to separate the different things. So you have sources that are nowadays mainly quantum dot sources, which need to be cooled down at cryogenic temperature. You have detectors, superconducting nanowire detectors, that need to be cooled down. But then you have the circuit, which can work at room temperature. So having them separated, it's nice, because you can work at room temperature with at least one element. But then scalability is also complicated. Once you go to having maybe thousands of mode, you start to have bundles of fibers, which are quite massive. So yeah, it's I don't have a clear answer on that. I would say in the short, medium term, I think having things separated will allow to optimize each of them without having to do compromises, while other people trying to have everything together, they need to compromise the performances. So they don't have the best detectors, they don't have the best sources, they have circuits that do not work exactly as they would. But maybe in the long run, we would have to integrate at least the detectors, I would say, on chip.
Okay, I think we don't have any more time for more questions, so I thank you again,
Thank you.
Professor Osellame.